Okay, the first problem is a little bit tricky because it contains some unnecessary information, which is really easy to add to infusion problems, I've found. It asks what the flow rate is in mils per minute to deliver 25 units of heparin in 1,000 mils D5W over an 8-hour period. So we're apparently administering the entire 1,000 mils over 8 hours. And so that gives us our flow rate right there. We don't need the 25 units in this problem. So that's something particularly to watch for in infusion calculations, is sometimes there's extra information you don't need. So really we have the 1,000 mils. We just need to know how many minutes. And so we have to convert the 8 hours into minutes. So 1,000 mils divided by 480 minutes, and that's 2.1 mils per minute. Next question is a 500 ml IV of D5W containing 2 grams drug is administered at 125 mils per hour. How many mgs per minute of drug will be delivered? So we're looking for the delivery rate. Sometimes it's nice to just write out everything we've got. This is 500 mils total volume. We have 2 grams of drug. We have a flow rate of 125 mils per hour. We've got all that, and what we're looking for at the end is milligrams per minute. And so the minutes are going to come from this unit here. So we could write this as 125 mils per 60 minutes. And then the milligrams will come from the total mass of drug. So 2 grams is 2,000 milligrams. And we can see that we'll probably use the total volume to get rid of the 125 mils. So let's go ahead and do that. We've got 125 mils per 60 minutes. So how many minutes to deliver 500 mils instead? And X I get for that is 240 minutes. So now we have the bottom. We have the number of minutes it takes to deliver the whole volume. And actually we have the milligrams too. We have 2,000 milligrams total. So 2,000 milligrams divided by 240 minutes, and that is 8 1/3 milligrams per minute. Okay, we have a second page of infusion problems here. This one involves determining time. So we have 500 mils of a blood transfusion that starts at 21:13, which is in military time. That means that we don't have any PM hours, so we just continue to count after 12 noon. So instead of 1 o'clock, it's 13, and then 2 o'clock is 14, and so forth. You count all the way around to 24 and then restart the clock. So it can be a little less ambiguous to use military time. A 500 ml blood transfusion starts at 21:13 at a rate of 30 drops per minute using a drop counter setting of 10 drops per mil. What time will the transfusion complete in 24-hour or military time? So let's write out what we've got. We have 500 mils total volume. There's 10 drops per every mil. 30 drops are delivered every minute. And we know we have a start time of 21:13. And what we want to find is the time at the end. And so you can kind of see a strategy looking through these values. I ordered them that way, actually. We have a volume. We can convert that to drops. We can convert those drops to minutes. And we can add the minutes to the time that we started to get the ending time. And so that's the value of writing out everything that you have, is you can sometimes formulate a strategy based on that. And so let's go ahead and follow that pattern. Let's start by converting the volumes in the total volume into drops. So this tells us there are 5,000 drops in the 500 ml volume. And then we can use that to determine the amount of time that will elapse to deliver those drops. So 5,000 divided by 30, that's 166 2/3 minutes. And then we have to figure out how to convert that to hours and minutes. And so I just start by asking how many hours in 166 2/3 minutes. So that tells me there's 2.7 forever hours. So that tells us the number of hours that elapse. And then let's go back and ask how many minutes the 0.7 hours are. And we see that there are 47 minutes if we round. So we have 2 hours and 47 minutes that elapse. So 21:13 is where we started. We add 2 hours and 47 minutes to that, and we get 24. So the transfusion will end at midnight, 2400 hours. Okay, so the final problem is weight-based dosing, and we're also adding a solution to the IV bag. So we have 10 mils of a 0.25 mg per mil solution that's being added to 100 mils of dextrose. And so what will be the rate of delivery in mils per hour with this weight-based rate? So let's start by calculating the weight. That may be easiest. We can ask how many kilograms is 45 pounds using our conversion table that we have in our head. And that is 20.45 repeating kilograms for that patient. And we can use that to determine the delivery rate. So we have 1 milligram per hour is the rate per kilogram. So what is the milligram per hour rate for 20.45 kilograms? And it's just 20.45. Okay, so next we can calculate what's the concentration of drug that's in the IV solution. We need to do that because we don't want milligrams per hour, we want mils per hour, and so using a concentration like mgs per mil will allow us to convert the milligrams to mil here. So the concentration is not directly given to us. We have an injection concentration that's added to 100 mils. We have to ask how many milligrams are delivered in 10 mils if the concentration of the injection is 0.25 milligrams per mil. So we see that we're going to be putting 2.5 milligrams into the IV bag. So we might think that that means 2.5 milligrams divided by 100 mils, but it's not, right? Because we've kept track of the fact that we add a volume to the volume of the bag. So we added 10 to 100. So the total volume on the bottom is actually 100 plus 10 mils, 110, to give us a concentration of 0.02, and then the 2 sevens repeat forever, milligrams per mil. Okay, we can now use this concentration to convert the milligrams up here into milliliters. So that might look like this. You could probably multiply it directly if you wanted to. Let's just continue with the proportions. 20.45 milligrams. How many mils is that? If we have 0.0227 milligrams in each milliliter. Answer is a nice even 900 milliliters. And so 20.45 milligrams per hour is the same as 900 milliliters per hour. And that's our answer.